This is the 12th Optimizing Compilers lecture. Today we're going to be looking at inference-based analysis. Just to recap from last time, we looked at constraint-based analysis, in particular our zeroth order CFA algorithm, where we develop constraints based on the syntactic structure of the program and then iteratively solve them to see how information flows around the program. And in particular, we were looking at how function pointers or function closures move around to indirect call sites. Today, it's a relatively short lecture on inference-based analysis, where we look at inference of types and other properties. And next lecture, we're going to develop it into a type and effect system. So a brief motivation. Essentially, we're looking at higher level program analysis in this part of the course. And we've already seen abstract interpretation and constraint-based analysis, which are two general frameworks for doing analyses of programs. In this lecture, we're going to look at an alternative framework called inference-based analysis. Now, within inference-based analysis, you have a set of rules for determining program properties. Okay. Now, typically, this property is a property of the entire program, and it depends recursively on properties of the program's sub-expressions. And what we have with inference-based analysis is a way of directly expressing those relationships. So essentially, we can use our rules to recursively compute the property, building it up from the very fine-grained up to the whole program level. So an inference system specifies judgments of this kind of form. Okay. Here, E represents an expression, which is, for example, a complete program, but it could be just part of a program, any expression within it. Gamma here is a set of assumptions about the free variables in E, okay? And phi is a program property. So what we're saying here, that under the set of assumptions given in gamma, E is some expression that has the program property phi. Let's look at the ML type system as a start, okay? Not the whole of it, but some of it. This particular inference system specifies judgments about a well-typedness property. So, based on this, we have, under the assumptions in gamma, the expression E has type T. Okay, here we've replaced our phi, obviously, with types. And we're going to avoid more complicated ML typing and just consider expressions in the lambda calculus. So, very simply, E could be some kind of variable, it could be, or constant, some kind of lambda abstraction, or some kind of lambda application. And our program properties are the types T. We've got an alpha, we've got an int, or we've got a T1 to T2. Okay, so very, very simple language here, just for looking at inference-based analysis. Gamma is a set of type assumptions in this case, because we're trying to prove the program property, the phi here, being types. We have type assumptions in our gamma. So what we have here is a set where what we say is that each identifier in that set is assumed to have the corresponding type. So x1 has type t1 and xn has type tn. We could have a totally empty gamma, or we could have quite a few different identifiers or expressions in that to have types already. We write this. So we basically take our gamma and put x colon t in square brackets afterwards to say that what we're doing with our gamma is we're adding an additional assumption into it. Okay. Should gamma already contain some assumption about x, then we're going to override that particular assumption and use the one that's in the square brackets already. So we use rules to inductively define what judgments are valid. Okay, and in a type system, of course, these are the typing rules. So let's have a look at some of these typing rules. Here's the variable typing rule. Okay, we're basically saying here, under the assumption that x has type t in our gamma, then x has type t. Okay, that's fairly straightforward. The lambda abstraction here, we're saying given that x has type t in our gamma and E has type t prime, then our lambda abstraction, lambda x.e, has type t to t prime. Okay, obviously it's taking an x of type t and it's producing a result of type t prime. And our lambda application, of course, here we say E1 has type t to t prime, E2 has type t, of course, and then applying the argument E2 to the lambda abstraction E1, we get type t prime at the end of it.